Greetings. So today we're going to talk about the heart as a pump. So we want to consider how it generates pressure and how that, by generating pressure, it's able to move blood in a unidirectional manner. So it distributes blood to the lung, and it can also distribute blood to the systemic circulation. So to do this, we'll first consider the structure and the function of the heart chambers and their associated valves. And then secondly, we want to talk about what's called systole and diastole. And systole is the time when the heart is contracting and generating pressure, an ejection of the blood. And diastole is when the heart muscle is relaxing, that the valves open and the heart fills with blood. The third, we want to explain the cardiac cycle, and that is that you have one systole and one diastole, and that's one cardiac cycle, and that's one heartbeat. And we want to talk about the associated heart sounds. And those are those sounds that you hear through the stethoscope, which is the lub-dub, lub-dub, lub-dub. And then fourth, we want to talk about what's known as the pressure volume loops, the stroke volume and the cardiac output. And these are ways in which we can address how well the heart is functioning. So it gives us some assessment tools for seeing how well the heart is acting. So let's get started. So the first thing is, as you recall, the last time we met, we said that the heart has a right side and a left side, and that on both sides, the right and the left, there are two chambers. The upper chamber is called an atrium, and the lower chamber, the ventricle. So we have a right atrium and a right ventricle. And we have a left atrium, which is shown here, and the left ventricle. And between the atria and the ventricles, at the base of the heart, we said there was the cardiac skeleton. And within this cardiac skeleton, there are valves. And there are four valves. We have two atrial ventricular valves, one on the right and one on the left. And then we have two other valves, one which is called the pulmonary valve, pulmonic valve. And this pulmonic valve allows blood to move from the right ventricle to the lung through the pulmonary artery. And the other valve is called the aortic valve, and that aortic valve allows blood to move from the left ventricle out to the aorta, which is a large blood vessel which distributes blood to the rest of the body. So the things to remember then are that we have these two chambers, and that the two chambers are going to move in a concerted manner. So we have blood moving in a unidirectional manner from one side, the right side, to the left side. And the amount of blood that moves from the right side to the lung is the amount of blood that returns from the lung into the left ventricle. So these two chambers then, the right and the left side of the heart, are in series, and so the amount that's ejected from the right has to be equal to the amount which is ejected from the left. The other thing that we should keep in mind, and that is that on the right side, the walls of the heart are fairly thin relative to the left side. And this is because on the right side of the heart, we are not generating as high pressures because the system that's downstream, that is into the lung, we're moving blood into the lung, does not have a high resistance. It's a low pressure system. So the right atrium generates about 10 millimeters of mercury when it's contracting, and the right ventricle about 25 millimeters of mercury when it contracts. The left atrium generates 15 millimeters of mercury when it contracts, and the right ventricle 120 millimeters of mercury when it contracts. And so therefore the left ventricle then is generating the most pressure within the entire system. And it has the thickest walls. It is the chamber with the thickest walls. One other point to remember, and that is that the blood is moving from the ventricles out through the valves, and the valves are located at the base of the heart. And so when the heart is contracting, the blood will move in this direction. So first we have blood entering into the right chamber, into the right atrium. It will move into the right ventricle, out through the pulmonic artery, and into the lung, and it goes out through the pulmonary valve, or pulmonic valve, and then it returns from the lung to our left atrium, When it enters into the left atrium, it moves through the AV valves, that's the atrioventricular valve, and into the left ventricle, and then from the left ventricle out through the aortic valve and into the aorta and out to the rest of the body. So a unidirectional movement of blood through the system. The valves are interposed between the chambers to prevent backflow. So this is what we see on this next slide. So we have the 4 cardiac valves, and they're to prevent backflow. So we want to always have movement of blood going from atria to ventricle, and from the right side of the heart going to the left side of the heart. The pulmonary and aortic valves prevent backflow from the arteries when the ventricles are relaxing and they have low pressure. And the valves in general are going to open and close due to changes in pressure across the valves, and that's true for all of the valves. So when there's a pressure difference between the 2 chambers, say for instance the atria has a higher pressure than the ventricle, then the AV valve will open. When the ventricle has a higher pressure than the atrium, then the AV valve closes. Okay, and the same is true for the aortic valve and through the pulmonic valve. The AV valves are the ones which experience the highest pressure. So these are the valves which are closed when the ventricles are contracting. And so those valves have an unusual structure attached to them, and these are chordae tendineae, and that's shown here on this diagram. They look like strings in this particular diagram, but they are tendons which are attaching those valves to the papillary muscles of the ventricles, and it's to prevent the valves from everting and allowing the blood to flow backwards from the ventricle into the atria as the ventricles are generating pressure. So unidirectional flow through the valves, and the valves close and open depending upon a change in pressure across the valves. All right, so let's consider our cardiac cycle. So as I said to you, the cardiac cycle consists of 2 portions. One is called systole, and this will be when the heart is filled with blood, and it then starts to contract and will eject it increases pressure and will eject blood. The second is called diastole, and diastole is when the heart is relaxing, the muscle is relaxing, and now the heart will fill with blood. Diastole is actually longer in a time period than systole for a given cardiac cycle. But one cardiac cycle has 1 systole and 1 diastole. So let's start the cardiac cycle where the ventricles are relaxed, the AV valves are open, and the ventricle is filling passively. This is passive filling because the pressure that's in the atria is higher than the pressure in the ventricle. So blood is passively flowing into the ventricle is filling. We now have an electrical event occurring, and that's our P wave. So the P wave simply is a depolarization of the atria, and when that occurs, the atria will contract, and as the atria contract, the pressure in the atria increase, and that expels a last little bit of about 20 to 30% of the blood volume into the ventricle. The ventricle now has a higher pressure than the atria, and the valve closes. So the atrioventricular valves will close. So the AV valve closes. At this point in time, we have a second electrical event, and that's called the QRS. QRS, as you recall, the QRS complex is when there is a depolarization of the ventricles. And following depolarization of the ventricles, we'll have contraction of the ventricles. And as the ventricles contract, they will increase pressure because now all the valves are closed. And so the blood that's within those chambers is isolated. And as the chamber volume gets smaller, pressure will increase on the liquid or the blood that's within the chamber. So isovolumic contraction simply means all valves are closed and pressure is increasing. The pressure eventually increases to where the aortic valve and obviously the pulmonic valves will open. And once that occurs, then the ventricles continue to contract, pressure is continuing to increase, and we have ejection of blood. Now, as the blood leaves the ventricle, the pressure within the ventricle drops, and as it drops, then it becomes less than the pressure that's in the aorta or less than the pressure that's in the pulmonary artery. And at this point, the valves will close. And so then we have all valves are closed, and this is where we have now a pressure is falling. And it is isovolumic. All the valves are closed, and the volume that's within the heart chamber is isolated. On the electrocardiogram, we have the T wave occurring. The T wave indicates the relaxation or depolarization of the cardiac myocytes, and following depolarization we have relaxation of the cardiac myocyte, and as they relax, the volume of the ventricle increases, pressure within the ventricle will decrease, and eventually the pressure within the ventricles now will be less than the pressure in the atria, and the AV valves will open. So during the time of isovolumic relaxation, all the valves are closed, the ventricle is relaxing, and the pressure is falling. Now, there is a very complicated way of looking at the ECG changes in the pressures within the left ventricle, changes with volume within the left ventricle, as well as the sounds that you hear with the heart sounds that you hear. And that's what's diagrammed on this particular chart. And this chart is called the Wigger's diagram. So if you understand the Wigger's diagram, then you understand completely the cardiac cycle. So let's just go through it fairly rapidly, and that is that this only pertains to the left ventricle. And then I'll go through it very quickly and then allow you to sort of come back and look at this, because as I say, if you study this and understand this, then you'll understand everything that's happening in the heart during a cardiac cycle. So if you notice, at the bottom we have our electrocardiogram, and at the top we have the ventricular pressure, and that is the pressure which is in the left ventricle. So that's the blue line. So we're going to follow this blue line, which is pressure, and over time. So this is time. And the first thing that we notice is that we have a P wave, and following the P wave, the passive filling that's occurring within the ventricle increases, and we have this sort of last little push, last little pressure increase, and that causes closure of the AV valves. Once the AV valve closes, the heart now, all the chambers of the heart are isolated. And at this point, we have the QRS. The QRS occurs when you start to get contraction, and as you have contraction in an isovolumic condition, the pressure rises. And that's what's shown here, until the pressure exceeds that of what's in the aorta, and that then causes the opening of the aortic valve. And as the aortic valve opens, we have ejection of blood. So the blood is now leaving the heart and entering into the aorta. Pressure continues to rise simply because we still have contraction of the ventricle. But eventually, we have a T wave, and when the T wave occurs, that causes the ventricles to relax. So at that point, pressure falls within the ventricle because enough blood has left. The aortic valve closes. The T wave occurs. We have relaxation of the muscle, and as we have relaxation of the ventricles, then the pressure falls, and this is an isovolumic relaxation, and that's what's shown here. At the end of isovolumic relaxation, the pressure now is less than what's in the atria, and the AV valve opens, and we again start to fill. So if you notice, while we had contraction, we have isovolumic contraction to isovolumic relaxation. This is called systole. So we have the isovolumic contraction and ejection at systole. And then when we start the isovolumic relaxation and eventually filling, that's the diastole. So that's what's shown at the bottom of the plot. The other thing that's added to this plot are the heart sounds. So the first of the heart sounds is what's shown here, and the first heart sound occurs after you close the AV valves, and this is called the lub of the lub-dub, lub-dub. So the lub is when you close all of the AV valves, and so now all of the valves are shut, and that isolates the ventricles. By closing the AV valve, the blood which is moving into the ventricle then sloshes back up against the valve, and you hear that slamming up against the valve, and that's what causes the first sound. So the first heart sound is closure of the AV valve and the beginning of systole. The second heart sound occurs when you have closure of the aortic valve. And as you close the aortic valve, again, the blood can slosh back up against the valve, and you hear this slushing against the valve, and that's the second sound. So first sound is lub, second sound is dub. So you have lub-dub, lub-dub. And that's one heartbeat. So for every, or one cardiac cycle, so for every lub-dub, that's one cardiac cycle. And in a person at rest, you have 60 beats per minute, so you have 60 of these cardiac cycles occurring every minute. If you start running and your heart rate increases to 180, then you have 180 of these cardiac cycles occurring per minute. And there's another way of looking at the changes that are occurring within the ventricles, and this is called the pressure-volume loops. So we diagram the pressure on the y-axis versus the volume. And again, we're only looking at the left ventricle. And let's only consider the black circle or the black loop, which is the A, B, C, D loop. So if we start at A, we start A, and the ventricle, the left ventricle, has 50 milliliters volume of blood in it. And as you go from A to B, then the volume increases to 90 milliliters. So AB is filling, passive filling, excuse me, of the ventricle. At B, now the ventricles has enough pressure that it closes the valve. And so once the valve closes, we now have the end of diastole, the end of filling. And at that point, we will now have isovolumic contraction occurring. So isovolumic contraction is from B to C. And we're increasing pressure, but there's no change in volume within the ventricle. At C, the aortic valve opens because we've exceeded the pressure that's in the aorta. Aortic valve opens. We continue to have pressure building up within the ventricle because there's still contraction of the ventricle. And that causes ejection of the blood, which is a loss of volume within the left ventricle. And we proceed from C to D, so this is ejection of the blood. When we reach D, then the ventricle has less pressure than in the aorta, and the aortic valve closes. And now we have an isovolumic condition where all of the volume that's within the left ventricle is constant. And the ventricle relaxes. So between D to A, we have isovolumic relaxation, and pressure falls, but the volume does not change within the chamber. So a couple of things to notice. So at B, B is called the end diastolic volume. And the end diastolic volume is the amount of volume that's present within the heart as it starts systole. At D, this D is called the end systolic volume, and the end systolic volume then is the amount that's left within the heart after we've had ejection of the blood. So if you notice, the heart's never empty, there's not a vacuum within the heart, there's blood within the heart. And under this condition, there's 50 milliliters present at end diastolic volume, end systolic volume. The difference between end diastolic volume, that is the filled volume, and end systolic volume, the volume after ejection, is called stroke volume. So that's the amount of blood that's been ejected from the heart. So end diastolic volume minus end systolic volume is equal to stroke volume. And in this case, it would be 90 milliliters minus 50 milliliters, or 40 milliliters would be our stroke volume. So we are interested in the end diastolic volume because it tells us how much volume is present within the heart, how big the heart is. And we're going to return to the end diastolic volume, stroke volume again, and systolic volume again in the later lectures. But given today, we'll just say that the end diastolic volume in each ventricle is normally about 125 milliliters, and during one systole, the volume of blood that's ejected, or the stroke volume, is usually about 70 milliliters. So since not all of the blood then is ejected from the ventricle, only part of the blood that's been filled into the ventricle is ejected. The volume that's remaining is that end systolic volume, and this is usually 55 milliliters, and that's what's shown here. So we have the stroke volume is equal to end diastolic volume minus end systolic volume. Now, the cardiac output is the amount of blood that the heart is giving to provide enough oxygen for all of the tissues. And the cardiac output has to vary depending upon the demands of the tissues of the body. The cardiac output is the volume which is pumped per minute, and it depends on both the heart rate and on the stroke volume. So cardiac output is equal to stroke volume times heart rate. And we said that the heart rate was typically about 72 beats per minute, and that the stroke volume is about 70 milliliters, and so that means that the cardiac output is about 5 liters per minute. Now, if you recall in our athlete, we said that the athlete could have a very low heart rate. This resting heart rate could be something like 35 or 50 beats per minute. But his cardiac output is about the same. His cardiac output is around 5 liters per minute. So how is he able to cope with having a cardiac output of 5 liters per minute and a heart rate that's only, let's say, 50 beats per minute? And the way that he copes is that the cardiac output is equal to stroke volume times heart rate. If the heart rate is 50 and the cardiac output is 5,000 milliliters per minute, this is 50 milliliters, then the stroke volume is the cardiac output divided by heart rate. So in this particular case, then, we'd have 5,000 divided by 50, or 100. So the stroke volume is equal to 100. And we said that a normal person, that the stroke volume is about 70 milliliters per minute, but in the trained athlete who has a lower heart rate, he has a larger stroke volume. And what happens with training is that the heart becomes stronger, the walls of the heart become a bit thicker, and the chambers can become a little larger. The heart grows and becomes stronger because it has to meet the demands of whatever the athletic event is. So they compensate by having a larger stroke volume, but they have a lower heart rate. And this is an advantage so that when they start at, say, 50 beats per minute, and they end up at 200 beats per minute, which is the maximum heart rate that the fellow can have, so that he's able to still fill the heart. Because if the heart rate gets too fast, you aren't able to fill the heart adequately. But if he starts with a 50 beats per minute and a large stroke volume, then he can move up to 200 beats per minute and be able to have a much larger ability to change or to vary his heart rate or his cardiac output than, say, I would, where I start with 80 beats per minute and a much smaller stroke volume. And again, I end up with 200 beats per minute as my maximum heart rate, but I have a shorter period for movement of my cardiac output. All right, so what are the key concepts then? So the heart consists of two separate pumps. Blood moves in a unidirectional manner from the right heart to the lung for gas exchange, then returns to the left heart from which it is pumped to the systemic circulation for delivery to tissues. Secondly, each beat of the heart, that's our cardiac cycle, starts with an electrical activation of the atria and then of the ventricle. And the sequence is the same on the right side of the heart as it is on the left heart. And thirdly, we have the ventricular contraction and ejection occurs during systole. And the beginning of systole coincides with the first heart sound and ends with the second heart sound. So the first heart sound when we're closing the AV valves, the heart is full, and the second heart sound where we are closing the aortic and pulmonic valve because the heart now is starting to relax and pressure is lower than what's downstream. Fourth, the ventricles relax and fill during diastole. And diastole begins with that second heart sound and ends with the first heart sound. So diastole is when the muscle is relaxing, pressure is falling, and we have passive filling with blood. Next, we have the volume of blood that's ejected with each beat is called the stroke volume, and that the sum of the stroke volumes ejected in 1 minute is our cardiac output. Okay, so the next time you come in, we're going to consider the cardiovascular system in more detail, so I'll see you then.